Generating digital outputs with an Arduino Uno is fairly straightforward. All you got to do is use the built-in function digital write. However, the Arduino Uno isn't capable of generating true analog outputs. All it can do is generate digital outputs, zeros and ones, lows and highs, 0 volts or 5 volts. There's some Arduino hardware out there that can, in fact, generate true analog outputs. These pieces of hardware have a device built on called a digital to analog converter, but the Arduino Uno doesn't have that. The best we can do is simulate analog outputs using a technique called pulse width modulation, and I talked about pulse width modulation in an earlier video. Today what I want to show you is what the pulse width modulated signal actually looks like using an oscilloscope that's being generated by an Arduino Uno. Alright, so that's what we're going to do today. We're going to generate pulse width modulated signals and take a look at what they actually look like on an oscilloscope. Okay, so I got an Arduino sketch here set up, and it's connected to, or the Arduino sketch is powering this Arduino down here that has the green LED attached to it. It's an RGB LED, so I'm only using the green LED right now, and it's connected to digital pin 10, okay, which is capable of generating pulse width modulated outputs. Okay, so over here, let's go ahead and upload this sketch. All right, uploaded the sketch, and the sketch is using analog write with a duty cycle of 50%. So the parameters specifying the duty cycle in analog write is 127. All right, so here is the LED, and I'll change it to analog write green 50, and we should see that it doesn't glow quite as bright. Okay. Or if I make it analog write green 5, now the duty cycle is going to be like 2%. So you can barely see it glowing right now. Okay, so now let's hook up the oscilloscope and take a look at the signal that is actually driving this LED. All right. Okay, so here's the oscilloscope hooked up to the digital pin 10, which is driving this green LED. And so let me change the duty cycle to 100% by changing the duty cycle parameter to 255 in the analog write command. You'll see that what this will result in is an always on signal. The voltage is always 5 volts. And if I make it 127, so that would be halfway between 0 and 255, so that's approximately a 50% duty cycle. This is what the signal looks like. Alright, so I don't know if you can see this very well, but I'm measuring the frequency of this signal, and it's a step function. It spends half its time high and half its time low, so that's a duty cycle of 50%, and the frequency is 490 Hertz, duty cycle 50%. Alright, if I change this to like 74, now the duty cycle is about 30%. But the frequency is still 490 Hertz. Okay, so the frequency is the same. What's changing here is the amount of time the signal is high in comparison to how much time it's low. So the period, and thus the frequency, is always the same. The period is about 2 milliseconds. It takes about 2 milliseconds for the signal to repeat. And so changing the parameter in analog write, all that does is change how long the signal is high during each period. Makes it bigger or smaller. Alright, if I make it, I do analog write on pin green, which is digital pin 10, and specify the duty cycle parameter is 10, now the duty cycle is about 4%. But the frequency is still 490 Hertz. Alright, and so now let me hook up the oscilloscope to digital pin 5, which is connected to the blue LED, and let me show you how the signal's different on digital pin 5. All right. Okay, so we're hooked up to digital pin 5 now, and so this is a pulse width modulated signal coming from digital pin 5, and here the duty cycle is also 50%. But digital pin 5 generates pulse width modulated signals at 980 Hertz, approximately twice the frequency as digital pin 10. So it turns out that most of the digital input-output pins on the Arduino Uno that can do pulse width modulation are going to generate a pulse width modulated signal that's 490 Hertz. But there's two pins, digital pin 5 and 6, which generate pulse width modulated signals at 980 Hertz instead of 490 Hertz. So why is that so? Well, they're just using, these signals are generated on board using peripheral devices called timers, and the timers that are being used to generate the pulse width modulated signals on pin 5 and 6 are different. Okay, so that is all I wanted to accomplish in this video, just show you on the oscilloscope what a pulse width modulated signal looks like. It's a step function, and it has a duty cycle that is defined as the ratio of the amount of time the signal is high, 5 volts, divided by the period, which is the amount of time it's high plus the amount of time it's low each cycle. All right, so I'll see you next time. Bye-bye.